This is Calculus 2 class. We're gonna study limit of sequence. Today's lecture. A sequence is a list of numbers that follows pattern. But what happens as we go farther and farther along the list? Do the terms settle towards one single value? Do they grow without bound? Or do they jump around? The idea is what is called the limit of sequence. By end of today's lecture, you will able to explain what it means for a sequence to converge diverge. Second, determine whether the sequence has a limit using rules and theorem. Finally, you can recognize common example of convergent, divergent of sequence. Before we jump into the formal definition of the limit of a sequence, let's look at the simple example and sketch it out. Consider sequence n over n plus 1, which meaning is an gonna be n over n plus 1. I can find a1, 1 over 2. I gonna plot that point on the coordinate plane. N equal 1 is right there, guys. A1 is y value. So I plot the point on the coordinate plane. The point gonna be 1, a1. Same thing is a2 gonna be 2 over 3, that's the second term, n equal 2, find the y value 2 over 3, this point represent 2, a2, n equal 3, a3 value gonna be 3 over 4, then you put the n equals 3, find the point 3 and 4, that's the y value. Then plot that point 3 and 3 over 4 right there. That's gonna be 3, a3. X coordinate on the sequence always natural number 1, 2, 3, 4. Y-axis represent the value of a sequence. Now that we've seen an example with the graph, sketch the sequence, let's give the formal definition, guys. An, that's the sequence, has a limit, which meaning is n is increasing. What is the behavior of an? An going to one point, getting close to one point, we say limit of sequence gonna be L. Another way say n approach to infinity, we're gonna say an approach the L value. So limit of an exists, we say sequences converge. Otherwise, we say the sequence diverges. That's we're gonna define the limit of sequence. Here is an illustration of convergence, guys. Look at this first sketch of sequence. Each point represents term of sequence as n is increase. So notice how this each term is getting close y equal to. Even though the sequence starts far away from the 2, as we move farther along, the terms clouded around this value, guys. That means we're gonna say limit of an approach gonna be 2. Another way say limit of an, sequence of an gonna be 2. That's we're gonna say that. Look at the second one, guys. The second one, another example of convergence. Sequence behavior a little differently from the first graph. So this one is go up, go down, go up, go down. but end behavior sequence getting close and close to the y equal 2. So we're gonna find this one is gonna be limit of an limit of an gonna be approach to the 2. That's how illustrate limit of sequence. Limit of sequence getting close to 1 point, we're gonna say sequence is convergent. Here is 2 examples of divergence. On the left, sequence oscillates. The terms bouncing back and forth. A1 is 1, A2 gonna be 3, A3 gonna be 1, A4 gonna be 3. So sequence bounce back and forth between the 2 values. There is never settle down the one value, one single value. This kind of behavior means there is no limit. So we're gonna say limit of an does not exist. We're gonna say does not exist. Go to the right. Look at this behavior of sequence. Sequence keep increasing. A1, A2, A3, A4. They keep growing larger and larger. That case, we're gonna say sequence gonna be diverge to the infinity. So limit an as an approach to infinity, they are going to infinity. So these are examples of divergent. We illustrate limit of sequence, convergent and divergent. What do you learn from the illustration? When a sequence is converged, they approach 1 point as n is increased. So now we're gonna find limit of sequence in the different way. First method is numerical method. So I want to find the limit of n. So an, general term is n, a1 is 1, a2 is 2, a3 is 3. We try a 100, 100. A 1000 is 1000. What kind of pattern you see? This sequence is increasing as n is increasing. So we're gonna say limit of an gonna be infinity. So let's have a second example. This time, negative 1 nth power. So an gonna be negative 1 and n. N equal 1 is negative 1. N equal 2, negative 1 squared. That's the 1. N equals 3, negative 1 cubed, negative 1. N equal 4, 1. Let's try n equal 9. Negative 1, 9, negative 1. N equal 10. A 10 is 1. This pattern of this sequence oscillating. Negative 1, 1, negative 1, 1, negative 1, 1. So this limit does not exist because they're not going to one single value. Let's have one more example with the numerical method. I want to find the limit of negative 1 nth power over n. So an gonna be negative 1 nth over n. Let's plug in the number. N equal 1, negative 1 and 1, negative 1. N equal 2, negative 1 square over 2, 1 over 2. N equals 3, negative 1 cube over 3, negative 1 over 3. N equals 4, negative 1 and 4, 1 over 4. What kind of pattern you're going to see? That's keep changing of a sign, guys. So a 9 is negative 1 ninth over 9 equal negative 1 over 9. A 10 is negative 10th power over 10, 1 over n, 1 over 10, guys. So this sequence getting close to which value? Can you see where they close to? I'm gonna say this an and it's getting bigger, getting close to 0, even though the sign is alternating. So limit of this sequence gonna be 0. Let's sketch the pattern of this sequence. See, A1, A2, A3, A4, they alternating sign, but they close y equals 0. That's why limit of this sequence gonna be 0. Another way to understand limit of a sequence is by looking at the graph of related function. Let's have first example. Limit n approach to infinity 1 over n. How gonna find this limit? We're thinking about related function to the 1 over n. That's fx equal 1 over x. I sketch rational function. Let's check end behavior as x approach to infinity. So x approach infinity and the behavior 1 over x getting close x-axis, which meaning is x approach to infinity 1 over x close to 0. So we find the limit of 1 over n that's also going to 0. Another example is find the limit of e to the n as n approach to infinity. So we take a function fx e to the x. Let's just sketch the function of e to the x. That's gonna be right there. So x approach to infinity and the behavior of f of x increasing. So we're gonna say limit of this sequence also increasing. So that's going to infinity, guys. Here is another example. So we want to find limit of e to the negative 1. So I'm thinking of a function fx gonna be e to the negative x. So I sketch the graph. Look at the end behavior, x approach to infinity. This function getting close to x-axis. So limit of this function as x approach to infinity, that's going to 0. So limit of this sequence as n approach to infinity going to 0. Another one is ln n. Limit of ln n. So we're gonna thinking of a function of ln x, then sketch the graph, then investigate and the behavior of ln x. So x approach to infinity and the v of ln x getting increasing, right? So that's increasing, so L going to infinity. So limit ln n and approach to infinity going to infinity. Sometimes when you try find the limit of a sequence, we end up with a fraction. That case, limit of fraction form, we can use L'Hopital, very powerful tool. So fraction of sequence, then we check the numerator denominator, that's going to infinity over infinity. Then we can apply L'Hopital rule. Let's have first example. N approach to infinity, n over n plus 1. N is increasing, numerator increasing, go to infinity. Denominator going to infinity, that's infinity over infinity. We can apply L'Hopital rule. Take a derivative n, that's gonna be 1. Take a derivative n plus 1, that's also 1. So limit of this sequence gonna be 1. That's really powerful rule we can apply when you have fraction form. So let's have another example, guys. Look at this. Limit n approach to infinity ln n over n. We already know ln going to infinity and going to infinity. So this is infinity over infinity. We can apply L'Hopital rule. Derivative ln n is 1 over n. Derivative n gonna be 1. This one is n approach to infinity. 1 over n gonna be, we know that. That's gonna be 0, guys. Here is another one. E to the n over n. So n approach to infinity. E to the n is increasing. N gonna be increasing. That's definitely infinity over infinity. We can apply L'Hopital rule. Derivative of e to the n, derivative of n gonna be 1. Now, this one is limit n approach to infinity, e to the n. E to the n go to where, guys? That's going to infinity. So limit of this sequence going to infinity. Let's have one more example for L'Hopital rule, guys. Look at this. Limit n approach to infinity n square over n plus 1 minus n square over n plus 4. So we want to find the limit of this sequence. So we have changed fraction form. So let's make same denominator. So we have least common denominator. So first term you times n plus 1. Second term we times n plus First one we times n plus 4. Second term we're gonna times n plus 1. So numerator gonna be n square n plus 4 minus n square n plus 1 over n plus 1 times n plus 4. Let's distribute n square times n cube, 4 times n square minus n cube minus n square. So you have this one. N cube is cancel out. 4n square minus n square is 3n square. So top is 3n square. Bottom, fold this bottom. N times n is n square. N times 4n. N plus 1 is n. 1 plus 4 is 4. So you have n square plus 5n plus 4. This is definitely infinity over infinity. So we can apply L'Hopital rule right there. Derivative of 3n square is 6n. Derivative of n square plus 5n plus 4 is 2n plus 5. That's again, this is infinity over infinity. You take a derivative one more time. Top is 6, bottom is 2. So limit of this sequence gonna be 3. That's really powerful tool to find the limit of sequence when sequence has a form of a fraction. The squeeze theorem is another tool we can use to find the limit of a sequence. Look at this sketch of the sequence. You have 3 sequences, AN, BN, CN. BN is, sequence BN is all the term of BN is between the A and CN. So we see BN is between the A and CN. Now, let's check the behavior of AN, guys. N approach to infinity. AN gonna be what happened? AN is behavior close to the L. So which meaning is AN approach the L as N approach to infinity. And look at the behavior of CN right there. So AN approach the L. Now look at the behavior of CN. CN go to where? That's going to y equal L. So Cn approach the L value too. Limit Cn gonna be L as n approach the infinity. How about the sequence in the between the two sequences? Let's check it out. So Bn gonna be behavior Bn and approach to infinity. What happened, guys? Look at the behavior. that's between the two sequence also approach the L. So we're gonna say limit of Bn go to L. That's the Schedul's theorem, guys. Bn is between the two sequence. Each sequence has a limit L, limit of An go to L, limit of Cn go to L. Then middle sequence has the limit L. That's the Schedul's theorem. Let's use Schedul's theorem to find the limit of one of m factorial. So let's find each value of term and we're gonna compare another sequence. So let's have Bn, that's another sequence we're gonna compare to An, that's gonna be 1 of n. So what is A1? I already give the sketch of two sequence. Let's find the one by one. So A1, 1 of 1 factorial. Factorial meaning is 1 factorial is 1. That's the 1. B1 gonna be 1 of 1. That's gonna be 1. Compare two sequence. So 1 and 1 same. That's the A and B is the same. A1 is B1 is the same. That's you're gonna plot on the graph. A1, B1 is the same, guys. Let's have the second term. A2 is 1 over 2 factorial. Factorial mean 1 times 2. That's gonna be 1 over 2. Let's find B2. B2 gonna be also 1 over 2. 2 value gonna be same. Again, so we're gonna plot on the graph. A2, B2 is the same. Find n is 3. A is 3 gonna be 1 over 3 factorial. Factorial meaning is 3 times 2 times 1. That's gonna be 1 over 6. How about the B3, guys? B3 gonna be, oh, I sketched A3 right here, guys, this point. Then B3. B3 gonna be 1 over 3. Let's find the B3 right there. That's the B3. Compared to value gonna be definitely B3 is bigger compared to 1 over 3, 6, 1 over 3. B3 is bigger than A3. Guys, can you see that? Let's do one more. A4, 1 over 4 factorial, which means 4 times 3 times 2 times 1. Here is a number. U times from 4 to 1. That's the factorial mean. That's 1 over 24. That's gonna be A4 is right there, guys. That's the value of A4. Now find the B4 is 1 over 4. I sketched the value of sequence is right there, B4. So compared to value, definitely B4 is bigger. That's gonna be relation between AN and BN. So now look at this one. 1 over n factorial, that's the AN, always less than BN. 1 over n, always greater than 0. Now let's take a limit and approach to infinity. 0 definitely going to 0, guys, right? How about 1 over n? 1 over n definitely going to 0. So middle, by Schedul's theorem, middle sequence have to going to 0. Can you see from the graph? That's AN getting close to 0. So that's why limit of 1 over n factorial gonna be 0 as n is increased. Let's have one more example for Schedul's theorem. I want to find the limit of sine n over n as n approaches to infinity. I'm gonna visualize this sequence, okay? So first, we know sine is bounded. Bounded meaning is sine n is always between 1 and -1, right, guys? Then sine n over n. You divide it by n both sides, negative 1 over n and positive 1 over n. So let's see the graph. Red one is sine x over x. Top function is 1 over x. Bottom function is negative 1 over x. Squeezing theorem say negative 1 over n go to some value, 1 over n go to some same value, middle part going to same value. That the squeezing theorem say to us. So let's find the limit of each sequence. First, limit n approach to infinity, negative 1 over n going to 0. Can you see from the graph? Also, this one is oscillating, but they close to 0. How about 1 over n? They also going to 0, so middle sequence has to go to 0. That's why limit n approach to infinity, sine n over n going to 0. There is an important property that connects sequence continuous function. So here is f is continuous, limit of sequence gonna be L. We can find limit of f(a)n. Limit can go into the function. Find the limit of sequence first, then evaluate the function that's gonna be f of L. Let's have first example, guys, right here, guys. So I wanna find the limit of cosine pi over n. Cosine function is continuous. This limit pass inside the function. So meaning is cosine limit and approach to infinity pi over n. This limit gonna be 0. We're looking for a cosine 0. Cosine 0 is 1. Because the cosine function is continuous, we can push the limit inside the function, find the limit of sequence first, evaluate the value later. Let's have another example. Limit and approach to infinity ln n minus ln n plus 1. We want to find the limit of this sequence. First, we have to use property of ln. So ln n minus ln n plus 1, meaning is ln n over n plus 1. We can rewrite this ln. So limit n approach to infinity ln n over n plus 1. ln function also continuous, so push the limit inside the function. So ln limit n approach to infinity n over n plus 1. This sequence has quotient form, so you can use L'Hopital rule. So derivative n is 1, derivative n plus 1 is 1. So limit of this sequence is 1. That's the ln 1. That's gonna be 0. This is very powerful property to find the limit with the continuous function. Now, let's look at the limit of geometric sequence. We want to know limit of geometric sequence. This is common ratio is R. Depends on the R. Limit of geometric sequence might converge, diverge. Let's check limit of sequence. First, R is 1. You plug in the 1. R is 1. 1 over n. 1 over n is always 1. That's gonna be, guys, look at this. R is 1. The R of n is always 1. That's constant. So limit of this sequence gonna be 1. R is between 0 and 1. R is between 0 and 1. For example, right there, I picked the R is 1 over 4. What happened here, guys? Limit n approach to infinity 1 over 4n. So let's use the numerical method. N equal 1 is 1 over 4. N equal 2, 1 over 2 square, 1 over 16. n equals 3, 1 over 4 cubed, that's 1 over 64. Also look at, see the behavior of this sequence. Getting close to what? Getting close to 0. So R is between 0 and 1. That's limit of this geometric sequence approach to 0. Now we need R is greater than 1. R is greater than 1. So we picked R is 4. We want to find the limit of 4n's power. You plug in n equal 1, 4n equal 2, 16n equals 3, 64. You also check the behavior of this sequence getting increasing. So R is greater than 1. Geometric sequence is increasing. We did R is greater than 0 in the previous slides. Now, what if R is negative? R is negative 1. Can you see that? You plug in the negative 1 in the R, then you have limit and approach to infinity, negative 1 and n. This oscillating, guys, alternating sign, alternating value, 1, negative 1, 1, negative 1. So this limit does not exist. What if R is between negative 1 and 0, guys? You pick the R is negative 1.5. So find the limit. Negative 1.5 n's power, you can see negative 1 over 2, 1 over 4, negative 1 over 8. So another way you check it, that's the alternating sign, but getting close to 0. This limit gonna be 0, guys, okay? So R is less than negative 1. I picked the R is negative 2. Limit of negative 2 to the n. Then pattern of this sequence gonna be negative 2, 4, negative 8, 16. So see that? Alternating negative 2, 4, negative 8, 16, but they gonna far from the 1 point. So this is, it does not exist. So let's summarize limit of geometric sequence. So limit of geometric sequence, ratio gonna be 1, the limit gonna be 1. Ratio gonna be between negative 1 and 1. The limit of geometric sequence gonna be 0, guys. You should remember that. Here is very powerful result about sequence called monotone convergence theorem. Monotone convergence theorem say every bounded monotonic sequence is convergence. Let's look at this illustration, guys. So this sequence AN bounded by 0 and m. So all the sequences between 0 and m, we call this is bounded. Also, behavior of the sequence. Look at that. What happened? Sequence is increasing. Then limit of this sequence getting close to certain value is L, which meaning is this sequence has a limit is L. Right, guys? This one is very powerful. Monotone convergence theorem gives us quick way to prove convergence without leaning to compute limit directly. We don't have to calculate, evaluate limit of a sequence all the time. Just we check sequence is bounded, sequence is increasing, then we know limit of sequence exists, they have a limit. let's have example of monotone convergence theorem. So we want to find the limit of a sequence a1 is 2, an plus 1 is 1 over 2, an plus 6. They don't show general term of a sequence, okay? So let's use monotone convergence theorem. What do you have to check? Sequence is bounded, sequence is increasing or decreasing. So let's find each term. A1 is 2. Let's find A2. A2 gonna be 1 over 2 and equal 1. That's the 2 is right there. A1 plus 6. A1 is 2. 1 over 2, 2 plus 6. 2 plus 6 is 8. Divide by 2, that's the 4. So you know the A2 is 4. A3, 1 over 3, A2 plus 6. A2 gonna be 4. 4 plus 6 is 10. Divide by 2 is 5. So A3 is 5. A4, 1 over 2, A3 plus 6. A3 gonna be 5. 5 plus 6 gonna be 11 divided by 2, 1.5. So one more time, A5, 1 over 2, A4 plus 6 equal 1 over 2, 4.4 plus 6, 5.5 plus 6, that's gonna be 11.5 divided by 2, 4.75. Can you see 2, 4, 5, 5.5, 5.75. This one is all the value of the sequence is between 2 and 6. That's the bounded. So we're going to say that's the bounded. But look at the pattern of sequence. 2, 4, 5, 4, 5.5, 5.75. Sequence gonna be increasing. So monotone convergence theorem say the limit exists. So let's find limit of this sequence. So we prove this sequence an bounded increasing. So they have a limit. So I put the limit of an equal a, guys. Now here, write down the an plus 1 equal 1.5, an plus 6. Now you take a limit to both sides, limit, and approach to infinity an plus 1, and approach to infinity 1 over 2 an plus 6. So let's distribute 1.5. So that's gonna be limit 1 over 2 an, 1 over 2 times 6. That's gonna be 3. Now, 1.5, take it out in front of limit, guys. Take it out. That's gonna be 1.5, limit and approach to infinity an. What is the limit of constant? That's gonna be 3 itself, guys. Doesn't change anything. That's gonna be 3. We want to find the limit of an, and the behavior an is the same. An plus 1, limit of an plus 1, limit of an is exactly the same. Okay? So this one is a, this one is a, guys. So we have a equal 1.5, a plus 3. Solve for this equation. That's gonna be 1 over 2, a equals 3. Which meaning is a equals 6. So limit and approach to infinity an equal a, we find the a equals 3. Limit of this sequence gonna be 6. We find the limit of this recursive sequence by using monotone convergence theorem. Monotone convergence theorem, you have to prove sequence is bounded and monotonic. What do you learn this session, guys, this lecture? First, sequence converges, it is terms settled towards a single value. The terms have to go to one single value. We say sequence is convergent. And we learn so many different ways to find the sequence. So you can use such as Schedul's theorem, Manhattan convergence theorem, property of continuity, and L'Hopital rules. So some case you can use L'Hopital rules to evaluate difficult sequence limit.